couples are applied on a bent bar as shown in the figure. Determine A. The magnitude and direction angles of the resultant couple, and B. The vector component of the resultant couple moments along AB, or the line AB. So what we have here are couple moments, and we know that couple moments are free vectors, so we can move them to act at a particular point. So if, say, we move them to act at the point O, we notice that these are all acting along a particular X or Y and Z axis. For example, there is 65 Newton meter acting on the Y axis. By the right hand rule, you notice that it will act in the positive Y axis, and the 80 Newton meter will act by the right hand rule. It will act in the positive X axis. The 95 Newton meter by the right hand rule will also act in the positive Z axis. So these will simply be, if we were to write these moments in terms of Cartesian vectors, we have 85 I for 85 Newton meter, then you're going to have 65 J for 65 Newton meter, and 95 K for the 95 Newton meter. These will be the couple moments in Cartesian vector form, and these can be added, easily added. The resultant will simply be MR would simply be 80I plus 65J plus 95K. That will be the resultant. And since the question is asking us to find the magnitude and the direction of the resultant couples, their resultant, magnitude of their resultant, we simply use this. It would simply be the square root of the square of that, and the square of that, and the square of that, and you find that your MR resultant would give you 140.18 Newton meter. And the magnitude of the resultant, and the for direction angle you simply go by, so alpha would be equal to cos inverse mx, which will be the x component of mr, and our x component of mr, the x component would be that one, the y component would be this one, the z component would be that. So for alpha, for example, we're going to have cos inverse over 80 over 140.18, and this gives us 55.2. That will be our answer. So by similar approach for beta, okay, so for beta theta, this will be my, and for gamma, this would be, here we have mz. So that's how you go about that. And says the vector components of the resultant couple moments along the line AB. So here what you're doing is simply determining the components of this moment vector along the line AB, similar to what we did with forces. And to do that, you have to determine the unit vector of the position vector of the line OA. So this line is AB. I don't seem to see B here, so this should have been the line AB. Okay, let's just take it as OA. So the line OA. So the line OA. So to determine the unit vector, let me use this. So we're looking at this line OA in this direction. That is our OA. So we're going to simply note that we assume this is 0, 0, 0, 0, and at A you're going to move 140 in the x direction, so 140 in the I, and in the y direction we're moving 120, so 120 I, and in the z direction negative 80. So that would be our coordinates at OE. So you find that your unit vector along the line OA would simply be UOA would be equal to 140 I plus 140 I plus 120 J. Sorry, this is 120J minus 80K over the magnitude of that position vector. This is 140 squared plus 120 J squared plus negative 80 squared, and you have your unit vector being 0.6965 I plus 0.5970 J minus 0.3980 K. That will be your unit vector. Okay, so remember that you're trying to determine the projection or the component of the resultant couple moment. Like in the case of forces, this is similar to the projection of this vector. Remember that the moment is also a vector. The projection of this moment on the line OA. So you have an expression like this. you have moment along OA will be equal to the unit vector OA dot product over our resultant moment. And always remember that we have our MR in Cartesian vector form. We also have our OA in Cartesian vector form. This is our OA, our unit vector OA, and this was our MR in Cartesian vector form. So when you apply the dot product, always remember that your answer is a scalar and not a vector. So you're going to by applying the dot product, your component of MR along OA will be equal to 5.6.7 Newton meter. Remember not to confuse dot products to the cross product. We normally use the cross product when trying to determine a moment about a particular point. For example, if we are trying to be given a force and trying to determine the moment, say about a point O, we make use of the position vector from the point. If this is our O and we've got a force acting in this direction, we can determine the position vector of this line joining the point O to the line of action of this force, at this point. So if let's say this was A, we'll determine the position vector of OA. The position vector we determine the position vector OA and apply a cross product with this force F. So cross product of R OA, you cross it with the force F, and these will be Cartesian vector form. So don't mistake this with the dot product.